Today we are going to discuss a very important property of Legendre's polynomial, and in fact this property is known as orthogonality of Legendre's polynomial, or you can say orthogonal property of Legendre's polynomial. So first of all we will define this orthogonality property of Legendre's polynomial and then we will prove it. So see here, I have mentioned this orthogonality of Legendre's polynomial. In fact, orthogonality of Legendre's polynomials is defined in this way, that is integral from -1 to +1 Pm of x into Pn of x is equal to 0 when m is not equal to n. But it will be equal to 2 over 2n plus 1 if m is equal to n. In fact, these two conditions we can write by a single equation in terms of Kronecker delta. So this statement can be written as integral from -1 to +1 Pm of x into Pn of x dx is equal to 2 over 2n plus 1 delta mn. In this delta mn, the subscript m and n definitely should be positive integers. It means you can say that these m and n are positive integers. And in fact this symbol delta mn is known as Kronecker delta. You have definitely studied the property of Kronecker delta. So you know this Kronecker delta mn has actually two values. It is 0 when m is not equal to n, and it is 1 when m is equal to n. So no, you know it. Now we will first of all prove this orthogonality of Legendre's polynomials, and after that in second lecture we will see some of the important problems in which this orthogonality property of Legendre polynomials will be used. So to prove this orthogonality property, we consider here two cases, and in first case we will discuss the value of that integral when m is not equal to n. And you have seen when m is not equal to n, then that integral is actually equal to 0. Now to prove this, as you know that Pn of x, which is in fact Legendre polynomials of degree n, and Pm of x, which is Legendre's polynomial of degree m. Actually, these Legendre polynomials are simply the solutions of Legendre's differential equation. You know it. And you know that the solution of any differential equation actually satisfies the differential equation itself. So if these Pn of x and Pm of x are the solution of Legendre's differential equation, then definitely they will satisfy Legendre's differential equation. And you know what is Legendre's differential equation? You know that it is 1 minus x square into y double prime. And as I have told you that this Pn of x is a solution, that is it is y. So in terms of this Pn of x, we can write the Legendre's differential equation in this way: 1 minus x square into Pn double dashed of x minus 2x into Pn dashed of x plus n into n plus 1 Pn of x equal to 0. Simply you can see that we have replaced the y by Pn of x. And the first two terms in LHS of this equation, you can see 1 minus x square Pn double prime of x minus 2x Pn prime of x. This can be written like this. You can check it. This may be written as d dx 1 minus x square into Pn prime of x. In fact, when you will differentiate this product 1 minus x square and Pn prime of x with respect to x, you will get the first two terms in this equation. You can see. And so this above equation has been written as d dx 1 minus x square Pn prime of x plus n into n plus 1 Pn of x equal to 0. And similarly, if you want to write the same equation for the Legendre polynomial Pm of x. So you should simply change the subscript n to m and we get the same result. And so I have written it here directly on the basis of this equation 1. We can write d dx 1 minus x square into Pm prime of x plus m into m plus 1 into Pm of x equal to 0. So these are the two Legendre's differential equations written in terms of the Legendre polynomials Pn of x and Pm of x. So now let us multiply the first equation. You can see here the first equation. This is your first equation. We will multiply this equation by Pm of x and this second equation by Pn of x, and then we will subtract this equation 2 from equation 1. So you can see I have mentioned here that multiplying 1 by Pm of x and 2 by Pn of x and then subtracting, what we will get. You can see after multiplication and subtracting 2 from 1, we will simply get that this is Pm of x. We will multiply by this Pm of x to the first equation, and you know the first equation is what? This is actually equal to, sorry, here is d dx. So here will be d dx operated on 1 minus x square into Pn prime of x. You can see the first equation, and plus n into n plus 1 into Pn of x. This was the original term, and we have to multiply it by Pm of x. So we will write here Pm of x. And as in RHS there is 0, so when you will multiply this 0 by Pm of x, the result will be simply, in fact, 0. So this will be simply equal to 0. You can see. And, sorry, we have to subtract the second equation after multiplying it by Pn of x. So right here that we will simply subtract from this the equation number 2 after multiplying it by Pn of x. So you can see this will be minus Pn of x d dx operated on 1 minus x square Pm prime of x. And due to this minus, this term will be also minus. So this will be minus m into m plus 1 into Pn of x into Pm of x. And since in RHS there was 0 in both terms, so this will be again 0. So you can see. Now, you can see we will actually now simplify this result to some extent. You can see here that this result may be written like this. This is d dx in operated on 1 minus x square and Pm of x into Pn prime of x and minus Pn of x into Pm prime of x. Pm prime of x. You can see, actually I have associated the first term in the first row and the first term in the second row. Now, let us associate the second term in the first row and the second term in the second row. So you can see this will be simply n into n plus 1 minus m into m plus 1 into Pn of x times Pm of x, because this is a common factor, you can see, and this will be equal to 0. Now we will simply integrate this result with respect to x from minus 1 to plus 1 for the limit minus 1 to plus 1. So integrating with respect to x from minus 1 to plus 1. You can see, since in the first term you can see there is d dx of this much. So when we will integrate it, we will simply get what? 1 minus x square times Pm of x into Pn prime of x minus Pn of x into Pm prime of x. So we will directly write it here. This is 1 minus x square into Pm of x into Pn prime of x minus Pn of x into Pm prime of x, and the limits are minus 1 and plus 1. And plus, now we will integrate this second term, you can see here. In fact, in this second term, this is a constant factor, n into n plus 1 minus m into m plus 1. So we will take it outside of the integral. So this is n into n plus 1 minus m into m plus 1. This is a constant factor, so I am taking it outside of the integral. And inside the integral will be what? This is integral from minus 1 to plus 1. This factor, Pn of x into Pm of x, this will be inside the integral, as they are actually the function of x. So this is Pn of x times Pm of x dx. Now you can see here, when you will put x equal to 1, see here, this 1 minus x square will be simply equal to 0. And when we will put x equal to minus 1, that is the lower limit, then again you can see that this 1 minus x square will be equal to 0. And here I have not written the RHS. Actually in RHS there will be 0. So this equal to 0. So now you can see the first term will simply vanish, because you have seen that when x is equal to 0, then this factor 1 minus x square will be 0. And when we will put the lower limit x equal to minus 1, then again this 1 minus x square will be equal to 0. So the value of the first term in this equation, after substituting these limits 1 and minus 1, will become 0. So now you can write that this result is 0 plus n into n plus 1. I am not turning over the page, you can remember it, and minus m into m plus 1 integral from minus 1 to plus 1 Pm of x times Pn of x dx, and this equal to 0. This is equal to 0. So now let us simplify first of all this term. You can see here this will be n into n, that is n square, and here m into m, that is m square. So you can write it n square minus m square, and plus now n into 1, that will be simply n, and minus m into 1, that will be simply minus m. So this factor inside this square bracket has been simplified like this, and after that we will write integral from minus 1 to plus m plus 1, and Pm of x times Pn of x dx, and this is equal to 0. Now you can see, in fact, this term n square minus m square, you can write it as n minus m into n plus m from the formula a square minus b square, and plus n minus m, and integral from minus 1 to plus 1 Pm of x times Pn of x dx, and this equal to 0. Now you can see that this n minus m term is in fact a common factor. So let us take this n minus m as a common factor. Then what will be about the other terms? This will be simply n plus m plus 1. You can see at the place of this much there is plus 1, and integral from minus 1 to plus 1 Pm of x times Pn of x dx, and this equal to 0. Now see that in fact in what conditions this equation will be actually valid. It means this 0 in RHS will be valid in what conditions. So actually this value 0 will be satisfied actually in two conditions. As you have seen that this n and m are actually integers, so even when n and m both are 0, then this factor will be not 0 because it will be 1. So actually this will be 0 when either this n minus m is 0 or the other factor Pm in this integral is 0. So equation 3 will be satisfied. When either this first condition n minus m is equal to 0, that is m is equal to n, or this will be satisfied when my integral minus 1 to plus 1 Pm of x times Pn of x dx is equal to 0. In fact, this is because this n plus m plus 1 is not equal to 0. So this equation will be satisfied either when this n minus m is 0, or you can say m is equal to n, or this integral vanishes. Only then this equation will be satisfied. But if you see what conditions we are actually considering here, actually we are going to discuss the situation when m is not equal to n. So in fact in this condition, if you consider that this m is not equal to n, then this equation 3 will be satisfied only when this second condition will hold. So you can say if m is not equal to n, then for the validity of equation 3, then equation 3 will be valid only when this integral from -1 to +1 Pm of x into Pn of x dx will be equal to 0. So you can see this is actually the first property of orthogonal property of Legendre polynomial. So we can write that this integral -1 to +1 Pm of x times Pn of x dx, this is equal to 0 if m is not equal to 0. And you can see that this is the first orthogonal property of Legendre polynomial. Now actually we will see the another situation or another case you can say, and in that another case we will consider that m is equal to n. So now let us consider the second case. Case number 2 is what? We will consider in this case that when m is equal to n. In first case we have considered m is not equal to n, and then you have seen that this integral from -1 to +1 Pm of x times Pn of x dx is equal to 0. Now we will see what will be the value of this integral when m is equal to n. So now we will find that value. Actually, starting with the generating function for Legendre polynomials, you can find the value of this particular integral in this case that when m is equal to n. So now let us start with the generating function formula for the Legendre polynomial. So from generating function formula of Pn of x, we have, you know what is generating function formula for Pn of x, you have already studied it, and in fact this is 1 minus 2xz plus z square whole to the power minus half, remember it, and this is equal to summation n equal to 0 to infinity z to the power n into Pn of x. You know it. Let us say this is equation 4. Now we will simply square this equation 4 both sides. So after squaring this equation, see this equation first of all seriously, because I will write that expression in another page so you can see this, and square this equation. So squaring both sides, you can say squaring both sides. When actually we will square it both sides, what we will get? We get, you can see, 1 minus 2xz plus z square to the power minus 1, because here was power minus half, so after squaring it will become minus 1. And in RHS you can see after squaring what will be our result. This is summation n equal to 0 to infinity and z to the power n Pn of x whole square. Now let us simplify this RHS. In fact, we are considering the case when m is equal to n, but we will also consider that m is in fact not equal to n here. So you can see this expression in RHS can be written as summation n 0 to infinity z to the power 2n into Pn of x whole square and plus, in fact this is in fact the similar terms, and now we will consider the cross terms. So after considering the cross terms, this will be 2 summation m equal to 0, n equal to 0, but remember m is not equal to 0 and up to infinity, and z to the power m plus n into Pm of x into Pn of x. Now after this step, we will simply integrate this equation both sides with respect to x between the limits -1 and +1. So you can say integrating with respect to x between the limits -1 to +1. We have what we have. You can see this will be simply summation n 0 to infinity and integral from -1 to +1 z to the power 2n. See here, Pn of x whole square dx, and this will sorry, here is plus sign actually, so plus 2 summation m 0, n 0 and m not equal to 0 to infinity, and integral from -1 to +1 and Pm of x times Pn of x dx, and this will be equal to what? You can see I am writing here, you can see, in fact I have written the term in RHS, in fact in this step in LHS. So now you can integrate this term in LHS, and this will be simply integral from -1 to +1, and this is dx over. In fact, when you will write this in denominator, then power will be +1. So this will be dx over 1 minus 2xz plus z square to the power 1. So I have not written here 1. So you can see actually this second integral, you can see here that if m is not equal to n, then actually this integral you have seen in the first part of the orthogonality property, that if m is not equal to n, then actually this integral of the cross term will vanish. So on the basis of first part of this orthogonality theorem, we can say that the second integral will vanish. So you can say this is simply summation n 0 to infinity integral -1 to +1 z to the power 2n and Pn of x whole square dx plus 0, because you can see in accordance with the first part of this theorem, when m is not equal to n, then that integral of Pm of x into Pn of x from -1 to +1 vanishes. So that term becomes 0. So you can write now this is equal to integral from -1 to +1 dx over 1 minus 2xz plus z square Now we will simplify this RHS now. You can see we can write that this is summation n 0 to infinity integral -1 to +1 z to the power 2n Pn of x whole square dx, and this will be equal to what? In fact, the integral of dx by 1 minus 2xz plus z square, you can say this integral is in fact 1 minus 1 over 2z ln 1 minus 2xz plus z square. This is the integral, and limits are -1 and +1. Now simplify the RHS of this equation. You can see this is 1 over -1 over 2z into. Now let us substitute the limit. As you know, in fact these are limits of x, so we'll simply put first of all the upper limit and then the lower limit, and so you can see what will be this result. This will be ln 1 and x is 1, so this will be in fact minus 2z plus z square and minus ln, see here 1 and x is now -1, so this will be plus 2z plus z square. So after substituting the limits, this is your result, and you can see that we can write it -1 over 2z, and see this expression 1 minus 2z plus z square, you can write it 1 minus z whole square. So this is simply ln 1 minus z whole square and minus ln. Now see this is 1 plus 2z plus z square, it means this is 1 plus z whole square. And you know that this will be -1 over 2z times. Now ln 1 minus z whole square will be what? This can be written as 2 ln 1 minus z, and minus again ln 1 plus z whole square, this will be written as 2 ln 1 plus z. You can see. In fact, you can take this 2 and this 2 as a common factor, and that common factor will cancel by this 2. So what will be your result? You can see this is simply this is minus 1 over z into ln 1 minus z minus ln 1 plus z. You can see. Now we will simplify this to some extent. When actually you will introduce this minus sign outside of this square bracket inside the bracket, then this term will become negative and this term will become positive. So you can write this expression in this way, and actually what is in our LHS, you can see in LHS was actually summation n0 to infinity integral from minus 1 to plus 1 z to the power 2n into Pn of x whole square dx. And what will be the expression in RHS, you can see here. As I have told you that you should introduce this minus sign inside the bracket. So this negative term will become positive and this positive term will become negative. So our result will be what? This will be simply 1 over z into ln 1 plus z minus ln 1 minus z. Now we will simply expand these ln 1 plus z and ln 1 minus z. So now expand it. So you can see this is 1 over z, and expansion of ln 1 plus z, you know what is this? This will be actually z minus z square over 2 plus z cube over 3 minus z4 over 4 and plus so on. And minus in fact now this will become minus ln minus. So since here will be actually all terms negative, so due to this minus you can write it plus z plus z square by 2 plus z cube by 3 plus z4 by 4 plus so on. And now you can see, in fact, this minus z square over 2 and this plus z square over 2 will cancel out. This minus z4 by 2 and this plus z4 by 4 will cancel out. So only the odd numbered power term will remain here. So, and this z and z will added, this z cube by 3 and this z cube by 3 will be added. So in fact this will become 2z, this will be 2z cube by 3. So you can take this 2 as a common factor. So this will be 2 over z into z plus z cube by 3 plus z to the power 5 by 5 and plus so on. You can see. Now actually we can take one of the z as a common factor. So when you will take one of the z as a common factor, let us see here, this will be 2z over 2 into 1 plus z square by 3 plus z4 by 5 plus so on. Now this z and this z will cancel out, and so you can write this as 2 into 1 plus z square by 3 plus z4 by 5 and plus so on. If you want to write the nth term, what will be that? That will be z to the power 2n and divided by 2n plus 1. You can see, because powers on z are even and in denominator there is odd number. So this will be the nth term. You can see here. Now if you want to write this expression inside the square bracket in RHS by the use of summation, what you can write? You can see easily. We will simply write it summation over n equal to 0 to infinity z to the power 2n divided by 2n plus 1. You can write it. So now let us see what will be our result. In LHS you have summation n equal to 0 to infinity and integral z to the power 2n, integral from minus 1 to plus 1, and Pn of x whole square dx, and this can be written as summation n 0 to infinity z to the power 2n into 1 over 2n plus 1. You can write it. In fact, I have told you, see here, that this expression in RHS can be written by the use of sign of summation in this form. Now see this equation, and you can equate the coefficient of z to the power 2n in both sides. So equating the coefficient of z to the power 2n on the both on the two sides. When actually you will equate these two. See here. In fact, in LHS, the coefficient of z to the power n is Pn of x whole square dx with integral from minus 1 to plus 1. So you can see in LHS, the coefficient of z to the power n is what? This is integral minus 1 to plus 1, and Pn of x whole square dx. And in RHS, what is the coefficient? The coefficient is, in fact, sorry, here actually there is 2. There is a factor 2 here, and I have mistaken here that there should be 2. 2 is a common factor. So this will be actually equal to 2 over 2n plus 1. And this is the result actually which we have to prove. You can see this result has been obtained when m is equal to n. M is equal to n. So now combining these two results, you can simply write that integral from minus 1 to plus 1 Pm of x into Pn of x dx, this equal to 0 if m is not equal to n, and this equal to 2 over 2n plus 1 if m is equal to n. You can see. and by the use of Kronecker delta, this result can be written in one equation. This is integral minus 1 to plus m minus 1 to plus 1, and in Pm of x into Pn of x dx. This is equal to 2 over 2n plus 1 delta mn. And so you can see this this orthogonality property of our Legendre polynomial has been proved. So this is actually the proof of this orthogonality property, but you should remember this property always, because whenever you will solve the numerical problems, definitely you will need the to write this orthogonality property of Legendre polynomial directly. So remember these things always. And in fact, as I have told you earlier, that in next lecture we will actually solve some of the important numerical problems based on this concept.